Hi, good evening. My name is Dinesh Vijayavardhana. Welcome to my program, www.engineerdesignerartist.com. So this is another video of my series of videos I posted before. So in my last video, I discussed about the conservation of mass principle. So this is a continuation from my last video. So let's look at what we exactly discussed in my last video. So we discussed the mass can be created or destroyed with the equation E equals mc squared, the Einstein's law. And then we discussed a continuity is a continuity conservation of mass principle. So that's the major topic that we learned from in our last video, which is the mass in. So whatever geometry we are in, so if it is a volume, a mass going in, the mass flow rate going in would be equal to the mass flow rate coming out. So in terms of time wise, if you don't have the time, it will be mass. If you put the time, a unit time, it will be mass flow rate. So now we further discuss the mass flow rate as the amount of flow in a unit, the amount of flow in a unit time, which is the equation is sigma a times v. The v is the mean velocity, and the rho is the density of the fluid. So usually in engineering we use water a lot, or sometimes air. So in a situation like that, the density would be the density of the fluid, and the A is the nominal, the area normal to the flow, that's the area, the nominal area, and the V is the mean velocity. For example, if you have a flow like this, the velocity profiles are like that, so the velocity changes all the time. So in a situation like that, it is the mean velocity that calculates the mass flow rate in that particular point. So if this is point A, the mass flow rate of point A equals to the mass flow rate rho times A times and the mean velocity at that point A. So that's mass flow rate, and then we further discuss into a volume flow rate. So volume flow rate equals the nominal area again, the normal area, so let's consider the A, and the mean velocity of A. So that if you consider that point A, the volume flow rate will be the nominal area times the mean velocity. So that is pretty much what we discussed in our last video. Now we're going to move forward into discussing it further. So let's erase this. Now, when you consider continuity mass flow rate, the con- cons- conservation of mass principle, conservation of mass principle. Usually, when engineering calculations, we need to make assumptions. So assumptions are the most common assumption we make is the steady state. So which means the flow remains the geometric level of the flow, the velocity streams remain same. So so steady state is very important for calculating mass flow rate or using the conservation of mass principle. And the second one is the incompressible flow. The fluid has to be incompressible in order to be the mass flow rate to be constant, or the volume flow rate to be constant, because for example, the water itself is an incompressible flow. So when you do calculations, it's always going to be easy. But let's say like air, for example, a compressor. So for example, a compressor. So in a compressor, air coming in, that's the inlet, air going out. So that's the compressor. So in a compressor situation, the air coming in, the density of the air coming in will be much lower compared to the density going out. So in a situation like that, which is the medium is air, which is a compressor, air compressor. So in a situation like that, the conservation of principle, mass principle, wouldn't apply. So we need to make sure that we use the right terms before we resolve the problem. So always important to make an assumption, steady state, or incompressible in order to use the conservation of mass principle, which we call sigma m in dot equals sigma m exit e m out, whatever you can use. So that's the conservation of mass. We also call this equation in engineering terms a continuity equation. Continuity equation. It's also called continuity equation. Continuity equation. Now, let's look at a problem. Let's look at a problem that just a general problem. In order for you to understand how these theories we learned over the last couple of videos, how we can apply that to the theory. So let's say there's a man who fills a water bucket. So there's a water bucket, right? And that water bucket is actually get filled by a hose. So he has a hose. So he has this horse. That's the man, and he has this horse, and he got this. So if you magnify this, that's like a nozzle. So that's the outlet. That's the inlet. That's the actually the nozzle, outer part of the nozzle, outer, and this is the inner part of the nozzle. So and so that's the hose. So it is didn't fill, the water bucket is getting filled by this man. And it says on the problem, the water bucket itself is it is 45 liters, so which is about 10 gallons, so 45 liters of the bucket. And the inner, also says the outer diameter of this nozzle is 0.08. It is in meters. I already did the conversions because it's easier. And the inner diameter is 0.02. That's the inner diameter. This is the outer diameter. So and it says this water bottle get filled within 50 seconds. So the time t to get filled is 50 seconds. So what the problem is, now they're asking what's the question A what's the volume flow rate and what's the mass flow rate of the stream at V in, V out. And then the second question is the Vm, which is the mean velocity of the stream. So now let's clear this out so we have more space. Now in order to calculate the velocity, not the velocity, the volume flow rate, we need to use V dot equals A times V, A times V, so the velocity. So now first we need to calculate. Now also in this problem that we need to make an assumption. So assumption means the flow is steady and also flow is incompressible. Alright? Just clear that out so we have more space. Now, and the medium we use in this problem is water, so the density is going to be 1000 square meters. 1000 kilograms per square meter. That's the density of the water. But now, in order to now we need to calculate the volume flow rate of the flow. So in order to get this water bucket get filled, so the volume flow rate is going to be equal to the amount of the total amount of water that is needed for the bucket, which is 45 liters. So if you convert that 45 liters, let's say the volume divided by total volume divided by the time. So total volume is 45 liters. For 45 liters would be, so 1000 liters is 1 square meter, 1000 liters is 1 cubic meter, 45 liters would be like that, and then divided by 50 seconds. So once we solve this, the answer will be 0.0009. So that's the cubic meters, and this is seconds. So that is cubic meters per second. So that's the volume flow rate pretty much at the exit where the nozzle exit is. So that's the volume flow rate. So that solves this problem. So that's one of the answers. And the second one is the mass flow rate. The mass flow rate can be calculated using so mass flow rate equals now let's look at before we calculate the mass flow rate, it's better to look at how we calculate the velocity, because when we look at the mass flow rate, we need to recognize that now so mass flow rate remains same. Mass flow rate equals rho A I V I or rho A E V E. So inlet diameter, inlet area, inlet velocity, outlet area, outlet diameter, and density. So the density remains same. So density remains same. Now let's calculate VE. So VE equals this is pretty much the volume flow rate. The mass flow rate divided by the density is the volume flow rate. So volume flow rate divided by AE. Alright? So a volume flow rate would be Now if you consider this part, so rho VE equals rho times, sorry, VE equals rho times B, sorry, so mass flow rate, let's put the rho back. So volume flow rate equals rho A E V E. And so in order to calculate the VE equals volume flow rate divided by rho A. Alright? So let's look at what the volume flow rate is. Now we calculate the volume flow rate as 0.0009 and the density is 1000, and then we have the area. So area we have to calculate is pi. It's a circular cross section is circular, so it will be pi r squared, the area. So pi times 0.008 is the diameter, 0.004 will be the radius, so pi r squared. So that comes down to VE, which is 17.9 meters per second. 17.9 meters per second. So that's our that we found in order to find the second mean velocity. We found the one velocity, so that's 17.9 meters per second. And now using this, now we can calculate the inlet. We can calculate the now what we haven't calculated now is the mass flow rate. Now the mass flow rate will give the answer. That's the exit velocity. Mass flow rate equals rho times, so it's a continuity mass equation, rho times V dot. So mass flow rate equals 1000 times this one. No, 0.009. So that equals 0.9 kilograms per second. So this mass flow rate will be pretty much, as we know, the continuity equation, the mass flow rate in equals mass flow rate out. So therefore, this mass flow rate will be inlet mass flow rate and outlet mass flow rate all the same, 0.9 kilograms per second. So we got the second answer. Now, the third point is that we need to find the inner velocity. Now, in order to find the inner velocity, let's look at inner velocity equals the mass flow rate divided by rho AI. So mass flow rate divided by rho AI. So that mass flow rate equals 0.09 divided by rho is 1000, and the AI would be pi 0.01, because that's the diameter, so we have to divide it by 2 to get the radius, times square. So that comes down to 2.865 meters per second. So you can clearly see that the outer velocity and inner velocity, outer velocity is much higher. The velocity at the exit, so let's re-put it here. That's the nozzle of the hose. So VE here is almost 18, so 17.9 meters per second, and VI, the inlet, is 2.86 meters per second. So you can clearly see that change of the geometry, the reduction of the geometry of the nozzle makes the velocity go faster. So what we can consider is that our next answer is the mean velocity. So the mean velocity within the nozzle is going to be you have to add these two. So let's the mean velocity, you have to add the inlet velocity and output velocity. So VI plus VE and divided by 2. So that is what is going to be mean velocity of the. But if you consider the velocity at the hose just before it reaches the inner part of the nozzle, it's going to be always going to be 2.86. But because they're asking for mean velocity at the nozzle, we have to 2.86 plus 17.9 divided by 2, which is, so roughly, so 2.86, 17.9, so it is 20.76 divided by 2, which is 10.38 meters per second. So that gives the answer B, 3.86. So we found the volume flow rate, which is 0.009 square meters per second, and the mass flow rate, which is 0.9 kilograms per second, and the mean velocity, which is the velocity at the inlet of the nozzle and the outlet of the nozzle divided by 2. So which is 17.9 plus 2.86 divided by 2, which is 10.38 meters per second. So this is just a simple problem how we can say, how you can solve a problem using a continuity equation. The most important thing is how to make an assumption, try to analyze the problem using that. So thank you for listening. Bye for now.